Aloha, this is Roger Brewer with the Hawaii Department of Health. This is a recording of a presentation I gave to the US EPA's Federal State Toxicology Risk Analysis Committee on September 22nd, 2022, entitled Field Study of Perfluoroalkyl Substances, or PFAS, in Wastewater Treatment Plant, Influent, Effluent, and Biosolids, Preliminary Data from Hawaii. This is a study we started a year or two ago in Hawaii to get a better idea of PFAS compounds, the makeup and concentration in wastewater treatment plant, influent, effluent, and biosolids, and in particular get some better idea of what potential risks were to the environment with respect to crop irrigation, drinking water resources, aquatic habitats posed by the use of the effluent or discharge of the effluent, as well as use or disposal of biosolids with respect to direct exposure to people in contact with the soil or leaching of PFAS from biosolids impacts to groundwater and also plant uptake. Our PFAS guidance is discussed in 3 different documents. The primary PFAS guidance is referred to as Interim Soil and Water Environmental Action Levels, or EALs, we refer to them, published in April 2021. The background of the models approaches used to calculate these action levels is discussed in the document Evaluation of Environmental Hazards at Sites with Contaminated Soil and Groundwater. In the collection of samples, processing, and testing is discussed in our technical guidance manual. Some other useful references for PFAS include the ITRC's 2020 document. I believe that was just updated a few weeks ago. You can see web pages below where we have another recorded presentation on our PFAS guidance, as well as recorded webinars on many other topics. So we've collected samples from 3 wastewater treatment plants so far. I plan on collecting samples from another 5, keeping the names and locations of these treatment plants anonymous for now. We haven't discussed the results with the operators of the treatment plant yet. They're all fairly small. The influent rate at treatment plant A, only 1.2 million gallons per day, about 30 tons of biosolids generated per week. It's a fairly old plant. They only receive commercial residential wastewater. There's really not much manufacturing in Hawaii. It's a fixed film biotower. Treatment plant B, a bit higher influent rate, 3.7 million gallons per day, generating about 150 tons of biosolids per week. It's still residential commercial wastewater coming in. Not really sure of the exact secondary treatment design on this plant. I think it's similar to plant A. Treatment plant C was the most recently updated plant, receiving about 2.8 million gallons per day influent, about 40 tons of biosolids generated per week. This is all in wet weight for the biosolids. In this case, again, residential commercial influent for the most part. And this is one of the more recently updated plants. They have an activated sludge system in place. One note here is that there's no landfill leachate disposed of at any of these wastewater treatment plants. Let's study objectives and methods. So when we do any type of these investigations, we'll try to be very careful about what we're specifically looking for. What's our question? In this case, we were only able to look at a day in the life of a wastewater treatment plant. So this isn't intended to represent what might be happening with respect to the plant over an entire year or anything. But for the investigation questions, in this case might be what is the average makeup and concentration of PFAS in the influent, effluent, and biosolids during a 24-hour period at the targeted wastewater treatment plant. It's pretty general, just for general characterization. We could have rephrased this in terms of risk and such, but for now, just want to get a general idea of what's there. Another question we're especially interested in is, are PFAS significantly leachable from the biosolids generated? So with these questions in mind and some of the data needs, first is we need the mean concentration of PFAS and the volume of influent, effluent, and biosolids generated over a 24-hour period. Also, we need to know the relative amount of PFAS sorbed to biosolids versus leached into a solution. We'll discuss this more later. So with respect to the data needs, then we go on to sample collection methods. For the water, we want to collect a continuous 24-hour sample. And all the wastewater treatment plants we work with have 24-hour samplers set up. So this is pretty easy to do. For the biosolids, we want to collect a single multi-increment sample. This is a sample made up of at least 30 increments, 1 to 2 kilograms. So we're going to collect a sample from a grid-like pattern from about 30 places within the biosolids. Then the sample is going to be air dried and then multi-increment subsampled at the laboratory. So they'll air dry it, spread it out to collect a subsample from about 30 points. And the subsample critically needs to be at least 5 to 10 grams. And the labs will do this with additional fee. The EPA's standard operating procedure for PFAS only calls for testing half of a gram of material, and that's just way too low to be reliably representative of the sample submitted. Labs can test a larger subsample. For this type of particle size and to deal with subsampling area, you need to get at least 5 grams, preferably at least 10 grams of the material. The laboratory we were working with was SGS Access Laboratory Analytical Services. If you're not familiar with decision unit multi-increment sampling methods, it's referred to on the mainland as incremental sampling methodology. Here's our guidance. We've been doing this in Hawaii far longer than anyone else. It started in 2004, so almost 20 years now. So we have in our technical guidance manual, sections 3, 4, and 5, a lot of details on how to, the background of the need for collect these samples, problems with discrete samples and such. In our web page, we have a 6-part DUMIS, so we refer to an investigation training series posted to our YouTube channel. And we have field studies of discrete sample error, just describing why discrete sample data aren't reliable, either for site characterization or risk assessment, really for any compound. We have a series of DUMIS case studies you can look at, and again, lots of recorded webinars on different topics. We targeted testing for 18 PFAS. These are the ones that we have toxicity factors for. The laboratory tested for more than these, and we also have physiochemical constants. So we have these, we can develop screening levels, or as we refer to them as action levels. You see here, I'm not going to go over all the names, but we list the compounds in anion form, not in the acid form, which you see, I think, in a lot of guidance. Anion form's what's more likely to be found in the environment. This actually comes into play when you're looking at the fate and transport of these compounds. Because the anion forms could be more or less soluble, more or less absorptive and such. Also, we found a number of additional PFAS that we don't have toxicity factors for and physiochemical constants for, so we can't really develop action levels. And you see a list here, a few of the sulfonamides, that especially interesting ones were the 5,3 and 7,3 fluorotelomere carboxylates. So we'll see those in the sample data in just a minute. We have toxicity factors, so we can develop toxicity-based drinking water action levels for the 18 PFAS. You see those listed here. These are all in part per trillion nanogram per liter. For PFOS, PFOA, we're still using some of the existing reference doses to develop action levels for these. We've looked at the newer drinking water advisories published by a group in USEPA. There could be orders of magnitude lower than this. Still not that confident in the reliability of the reference dosage used, the applicability, so we need to look at that in more detail. Also, we have chronic aquatic toxicity action levels for, a shorter list of the compounds here. These were mostly compiled by the state of Washington. So they've got a great ecology group, the Department of Ecology with the state. So our soil action levels. So again, the 18 compounds listed, action levels for direct exposure. These are based on non-cancer hazard to young children aged 0 to 6. You can see these are all most of them in the low part per billion range. And then the second column is leaching to drinking water aquifers. These even lower in the single digit for a number of them, even below a single digit for potential leaching of these compounds and contamination of groundwater. We use a model here referred to as sea soil, a generic leaching model. I don't have a lot of confidence in the model, especially for PFAS. In our experience, it tends to overpredict leaching risk. Our direct exposure action levels are based on approaches. It's a combination of approaches developed by EPA and other entities. These are all discussed in our PFAS guidance reference I gave earlier. And once you exceed an action level in soil for leaching concerns in our guidance, the next step is to run a leaching test on it. Right now, the main test we're using is referred to as the synthetic precipitation leaching procedure, SPLP. If you're familiar with TCLP, this is similar. You take a spoonful of dirt, essentially you put it in 2 liters of, in this case, fake rainwater, shake it up for a few hours, and before you do that, you would have measured the concentration of the compound in the soil, so you know the mass of it in the sample you put in the solution here. And then you compare the mass of the contaminant that stayed in the soil to what leached out into the water, the SPLP solution. You can calculate a desorption coefficient, or more of a desorption coefficient, or KD value. Now these tests, the SPLP tests, tend to be misused quite a bit in the environmental world. The data for the solution itself, the water solution, was never intended to be compared to some type of water-based action level, either drinking water or aquatic toxicity. These tests are to be used to calculate sorption coefficients. We'll look at that in more detail in a minute. Then you input the sorption coefficient into an equilibrium partitioning model, and then you can estimate what the concentration of a contaminant might be in the source area leachate. A better test to run reflects more of what we're interested in the field is a soil column leaching test. In this case, you pack a column with soil from your targeted area, targeted site, and then you pump water up from the bottom of the column and out through the top. Pumping it up from the bottom just pushes the air out. And as the leachate comes out the top, then you test it. Now, in both these cases here, you might see these leaching tests we ran on some of our samples. The leachate was fairly turbid, so we had to filter them before we sampled. So the soil column test, I prefer it. It matches the question in the field. So the question in the field might be, say you have a targeted agricultural field where you've applied biosolids. So again, going back to coming up with a reasonable investigation question, the question in this case might be, what's the concentration of some PFAS compound in infiltrating irrigation water through this agricultural field? And you have to add a time period to it, say over a 1-year period. So imagine it, you're irrigating a field over a 1-year time period. If you could collect all the water that infiltrated through that biosolids emitted soil, collect all of the leachate in a single tank and test it, that's the answer you're looking for. And the way you would do this then is you would collect a really good soil sample from the field. It has to be a multi-increment sample. You can't use discrete samples in either one of these approaches here to look at leaching. So you collect a really good sample, 1 or 2 or 3 or 4 kilograms, pack it in the column, and then you pump an equal amount of water through that column that would equal a 1 year's worth of irrigation. Irrigating fields here in Hawaii typically use about 120 centimeters of irrigation water, infiltrate through it. So you could pump that much water through the column, and then you test the water coming out. The standard EPA test, the LEAF method 1314, calls for testing the leachate 9 times, which it's interesting from a science standpoint. You can look at how the PFAS may vary over time, but from our question in the field, we just want one sample. We want one number. What's the concentration of the PFAS in the leachate migrating, infiltrating irrigation water going through the field over a 1-year time period? So we want one test. That's one thing we're working on, is a way to modify this test to bring the cost down and to more directly address the questions that we're asking. We didn't run too many tests in this particular study I'm going over this time. We were just getting it set up. We may want to run more than one test of leachate. We may want to look at the first flush, but in general, we'll test the leachate 1 or 2 times. So back to the SPLP test. Once you get the data, then you calculate a sorption coefficient. This is from a document, 1992 USEPA document, batch test procedures for estimating soil absorption of chemicals. So the KD factor is calculated as the ratio of the concentration of the contaminant absorbed in the soil divided by the concentration of the contaminant in the leachate. Now when this ratio starts to approach 20, then that's when the contaminant we would consider under our guidance as being fairly strongly absorbed, not significantly mobile. This is when the retardation factor for the contaminant migrating through the soil is going to approach about 100. So think about this. On the right is the colored columns, predicted mobility and soil leachate. These are based on the published sorption coefficient, KOC value for these individual compounds times a default organic content of the soil. So contaminants like MTBE, PC, atrazine, perchlorate, or whatever have very low KD values, less than 1. This is what you see making up plumes, especially in groundwater. Other contaminants like diesel fuel has a moderate KD factor between 1 and 10, so more moderate leaching potential. That's why you don't see diesel plumes getting that far. Dieldrin, another organochlorine pesticide, the KD factor is between 10 and 20. So now you're getting these contaminants are getting fairly strongly absorbed to the soil. So you're not going to see a lot of plumes or leaching risk from these contaminants. Once you get over a factor of 20, these are applied to contaminants like DDT, PCBs. You don't see a lot of plumes of these contaminants in groundwater because they just bind too tightly to the soil. And you see contaminants like dioxin and benzoypyrene. Now the KD factor is getting up into the hundreds. So we discussed this in our guidance we published in 2017, use of laboratory batch tests to evaluate potential leaching of contaminants from soil. We have a spreadsheet you can use to calculate KD factors for individual compounds. That's the background. Let's look at some of the data from the sites. This is wastewater treatment plant A. So you see influent, effluent, biosolids, and then the leachate. So for this particular plant, this is a fairly old wastewater treatment plant. It's not getting any leachate from landfills, but look what's coming in the influent. Most of it is the 5,3-fluorotelomere carboxylate. And I've seen some references suggest if you see this FTCA in your influent, it's an indication of landfill leachate. Well, that's definitely not the case for here. And then the other main component was the hexanoate. Concentrations here are pretty low, 40 nanograms per liter. Look at the effluent. The effluent looks like the influent. The same thing, 5,3 FTCA, and then the hexanoate. And I wonder if this is because the plant's really old and there's not much treatment going on. I'm not really sure. The biosolids on the upper right, these are for the biosolid samples they were dried, sieved, and subsampled. They're dominated by the fluorotelomere carboxylate again, 5,3 TCA, and you see the 7,3 FTC TCA, some sulfonamides, and then a lot of other compounds in the biosolids that we didn't detect in the water samples. In the leachate solution, SPLP solution, dominated by 5,3 FTCA. You see all the numbers there in red, the other compounds. What that indicates, the KD factor for these compounds was over 20. So these are coming out in the solution, but we don't expect these to be very mobile. You can think of them kind of like ping pong balls covered in Velcro. They may break free. They're not going to get very far in the soil before they stick to some other soil particles again. That's what the KD factor is telling us. Here's wastewater treatment plant B. In this case, the influent looks pretty similar. It's dominated by 5,3 FTCA and the hexanoate again. Again, there's no leachate from landfills coming into this plant. Look at the effluent. In this case, there's no FTCA, or at least it wasn't detected. Detection level was 10 nanograms per liter, but now it's dominated by a pentanoate. So maybe this has something to do with the treatment process within the plant. I'm not sure. We haven't really looked at this in detail. Biosolids look pretty similar, dominated by the fluorotelomere carboxylates again. You see the sulfonamides, and there's some PFOS showing up, and then a whole host of other PFAS compounds in the biosolids. The leachate in the SPLP solution, again, looks very similar. In this case, the KD factors for some of the compounds, including the 5,3 FTCA, and then the butanoate, the heptanoate, and the hexanoate, were all less than 20, which suggests they pose a slightly higher leachate risk. We'll look at that again in a minute. Again, just because this stuff's coming out in the SPLP solution doesn't mean it's going to be in the leachate that escapes from the, say, biosolids emitted soil. Here is wastewater treatment plant C. Well, now this looks different again. there's no 5,3, there's no fluorotelomere carboxylate in the influent, at least it wasn't detected above the detection levels. It's dominated again, a lot of hexanoate, but now you get the butanoate and the octanoate and the pentanoate dominating the influent. The effluent, oddly enough, though, looks similar to the previous plant. There's a lot of pentanoate in there and the hexanoate. So again, maybe this has something to do with the way that it's being processed. Not really sure yet. The biosolids again look similar. It's the fluorotelomere carboxylates dominating again. This time you're getting some decanoate showing up in the biosolids. And again, a whole host of other PFAS compounds in the biosolids. In leachate solution, SPLP solution, there again is the 5,3 FTCA and the 7,3 FTCA dominating the SPLP solution. You see there, at least those compounds this time are highlighted in red, which means the KD factor for the compounds is greater than 20. We wouldn't expect them to be very mobile, very leachable out of the biosolids. There was some butysulfonate and heptanoate in the biosolids. The KD factor was less than 20, so potential leaching risk. When we compare the data to our action levels for the influent and effluent, none of the PFAS exceeded our action levels for drinking water. Now in this case, for some of the precursor compounds, we were just looking at what we expected to be the final endpoint compounds and comparing the data to action levels for those compounds. So nothing exceeded in drinking water, nothing exceeded in aquatic toxicity for any of the PFAS compounds. For the biosolids, looking first at direct exposure, so kids playing in this stuff. In the wastewater treatment plant A, none of the PFAS compounds exceeded our biosolids action levels. So again, all the action levels were quite low, as you saw. In treatment plant B, the decanoate was slightly above our action level for direct exposure. Treatment plant C, decanoate and dodecanoate, again, slightly above our action level for direct exposure. If you did a more detailed risk assessment on this, then the cumulative hazard index for these compounds is going to be way less than 1. It doesn't look like the biosolids or the PFAS and the biosolids, at least for these specific 3 plants, pose much of a direct exposure risk. It was leaching to groundwater, though. A number of the PFAS compounds got flags exceeding screening levels, or if we apply the endpoint compound action levels to the precursor compounds. A lot of potential leaching risk. So that's something we want to look at in more detail. Here's why we looked at that. Here's wastewater treatment plant A, biosolids predicted versus measured absorption coefficients, KD factors, and potential leaching risks. So on the y-axis, we have the predicted absorption coefficient, and I only plotted the PFAS compounds that we have toxicity and physicochemical constants for. On the x-axis is what we actually measured in the biosolids. So you can see for treatment plant A, all of the PFAS compounds, the KD factor was greater than 20, which suggests these compounds are fairly tightly bound to the organic material in the biosolids, not significantly leachable. Interesting thing here is maybe science actually does work. You can see the longer chain compounds have the highest KD values, and as you move toward the origin of the graph here, you get into the shorter and shorter chain compounds have lower KD values and pose a higher leaching risk, or at least more mobile. In this case, though, still not very mobile. I put up here the measured values for the fluorotelomere carboxylates, 31 for 5,3 FTCA, 157 for 7,3 FTCA. Above 20, these compounds, based at least on the SPLP test, shouldn't be that leachable from the soil, from the biosolids. That was A. Here's treatment plant B. Looks pretty similar. You get the longer chain compounds, very high, measured and predicted absorption coefficients. And some of the shorter chain compounds, in this case, actually the KD factors were less than 20 for hexanoate, and then for heptanoate and butanoate. So based on the KD factors, these compounds for this particular biosolids, this particular sample, could be potentially leachable. Still not that low. So they're still fairly tightly bound up. FTCA, 5,3 and 7,3, you see the KD factors posted here. For 5.3 FTCA, the KD factor was slightly less than 20, so it's slightly mobile, but still pretty tightly bound up in the biosolids in the organic material. This treatment plant C, again, is the same thing we're seeing as the longer chain compounds, higher measured and predicted KD factors, shorter chain compounds, lower sorption coefficients, and both predicted and measured. In this case, several of the PFAS compounds, pentanoate, hexanoate, butysulfonate, all with KD factors between 10 and 20. Again, not that mobile, but potentially mobile. And then the FTCA here, 5.3, slightly above the 20 cutoff we use. 7.3 FTCA again is 63 KD factor, so it's well up into the range where it's not going to be significantly mobile. So interesting observations. Again, we're just getting started with this. A lot to think about. So in summary, and this is definitely in progress. And took a lot of notes from other presenters at this conference. Also, there's some great people talking about biosolids in general and the use of biosolids in agricultural fields. Again, in this study right now, we're showing it's data for a single day, just 24-hour time periods. And next month, it could be different, probably different between rainy seasons, dry seasons. We don't know. We need to do some longer-term studies. We need to get some toxicity and physiochemical factors for the precursor compounds. They're dominating the biosolids. They're very critical. And something we discussed before is you can't just look at PFOS and PFOA. If you do data for that, then you could be missing quite a bit of risk posed by these compounds. The PFAS makeup of influent, somewhat variable between wastewater treatment plants. It'd be interesting to look at a lot more plants, get a better idea. Now, the presence of the 5.3 FTCA in influent is not related to landfill leachate in any of these wastewater treatment plants we looked at, even though I know this has been suggested based on data for landfills on the mainland. The PFAS makeup of the effluent, I'm sure it reflects the wastewater treatment plant design. It's something we need to look at in more detail. In the influent and the effluent, the drinking water action levels for PFAS weren't exceeded, so the PFAS don't seem to be posing a drinking water risk. Not that in Hawaii, at least, they don't really threaten drinking water. Most of the sites, biosolids and wastewater treatment plants are on coastal areas. Same thing for fire training pits. Also, the aquatic toxicity action levels weren't exceeded in the influent or effluent. Not so much of a concern there, at least for chronic aquatic toxicity. We haven't looked at biouptake much yet. The PFAS makeup of the biosolids was pretty similar. That's interesting to think about. All these longer chain compounds are really getting bound up as expected in the biosolids. So the PFAS in tested biosolids at least do not appear to pose significant direct exposure risk if these biosolids happen to be applied to parks or ag fields or residential areas. Most PFAS appear to be tightly bound to organic material and not significantly leachable. So sorption cap factor coefficient greater than 20. Shorter chain compounds could be moderately leachable. This is interesting because some of the presentations where someone from Oregon was talking about the application of biosolids in ag fields, and they had groundwater data showing the groundwater was contaminated with some of the biosolids. Well, how did it get there? Based on our leaching tests, the stuff is pretty bound up in the biosolids, but keep in mind these biosolids are about 85% water. So my initial guess, anyway, assuming our sorption coefficients are in the right range, is that contamination of groundwater from application of biosolids to agricultural fields, it's probably due to PFAS in the water content of the biosolids. So they're just diffusing into the irrigation water and then getting carried down into the groundwater, rather than actually having the PFAS bind to the biosolids and then be stripped from the biosolids in leaching. But we need to do more tests in this. So this is a pretty quick summary, initial introduction to studies we're doing here. We're always open to new ideas, so please contact us if you're interested. And we'll be carrying out the rest of the study toward the end of 22 and probably into 2023. And I expect we'll be doing these type of studies for several years now. Thanks.